suppose you want to give someone a proof. Okay, so, usually when people think about proofs, they think of mathematical proofs where you just verify kind of line by line. But suppose that your goal is to give a proof that reveals no information about why the theorem is true. So you want to convince someone that the statement or the theorem you're trying to prove is correct, is true, without revealing any additional information beyond the validity of the actual statement. This is what zero-knowledge proof is. Now, what I told you right now is an intuitive notion. You don't want to reveal information. What is reveal? What is information? What needs to make that precise and mathematical? So that's kind of the beauty in this work. How do you make it precise and mathematical?
The proof does not reveal anything except the fact that the theorem is true. Namely, proofs that you learn nothing from. And they call these zero-knowledge proofs. You learn nothing from the proof except that it's true. By the paradoxical nature of this, in which in normal proofs we expect that the proof reveals a lot. In fact, the way people are doing mathematics, sometimes you are more interested in the proof, in the techniques, you want to learn from proofs. They suggested that maybe for some theorems there might be proofs that are convincing with extremely high probability, but do not reveal any information about the proof besides the validity of the theorem. And it's sort of strange to say the least, or strange because we never expect to convince anybody in anything if we don't tell them something they didn't know. Anything that has a proof also has a zero-knowledge proof.
And in order to do that, they actually needed to change the way we even think about proofs. So even though proofs were studied for thousands of years already in ancient Greece, starting from 85 and from kind of this idea of zero-knowledge proof, in order to construct these proofs, they changed the model. They changed the way we even think about proofs. And instead of having proofs where you kind of verify line by line, in their model, proofs are actually an interactive process.
The person who wants to learn the truth or catch the error in a proof is a verifier, and he or she can interact with the prover, not just receive a proof, but actually ask questions and maybe randomize the process and ask different questions different times. And at the end of the process decide whether the theorem is true or not. But if the theorem is true and the proof is correct, nothing will be learned by this verifier. So this is called a probabilistic interactive proof, this interaction, and which allows a small amount of error that depends on the verifier. The verifier can reduce it as small as they want.
So a proof is kind of verifier dependent. It's for a specific verifier. So if I'm the prover and you're my verifier, the proof is an interactive process between the two of us. Not only is it interactive, it's a randomized process. So you as a verifier toss coins, kind of. It's a randomized interaction. And in addition, it doesn't give you the full kind of soundness guarantees that traditional proofs give you, which is, if the proof verifies, you know the statement is true. However, in kind of these interactive proofs, your only guarantee is if you accept, if kind of the proof verifies, then the theorem is true with very, very high probability. With probability 0.9999, you can make it as close as you want to 1, but it's not actual 1. So it's a very different type of proof system, and they defined it in order to kind of, they consider this proof model because in this model, they can define what zero knowledge is rigorously mathematically, and they construct such a proof. So actually what they proved is kind of a miracle, in my opinion, statement, which says any proof, any mathematical proof, can be converted into zero knowledge one.
I cannot go to too much detail about how you prove things in zero knowledge, including the Riemann hypothesis or but I'll just say that the first thing to realize, which was easy to any computer scientist, is that you need to prove it only for one theorem. There is a universal theorem. The key word is NP completeness. You can take any complete problem and prove statements in this language. For example, the one we use is that map coloring. Whether a geographical map, I give you a map and I ask whether it can be colored in 3 colors legally. So borders don't. I'm sure most of you know that 4 colors are always enough. 3 colors are not always enough. And so it's a computational problem, and it's a hard problem. It's an NP-complete problem. But if you find zero-knowledge proofs for this type of statement, that the map is 3-colorable, then you automatically, because of the theory of NP-completeness, you have proved in zero-knowledge anything else. So this is a task. And then how do you do that? Well, it involves cryptography, as I said, and it has to do with not giving the colors, but giving encryptions of the colors. And in the process of interaction, revealing very little, like the colors of 2 countries which are adjacent, but you open only these envelopes to the verifier and show them that they are different colors, but not open anything else. And this reveals essentially no information.
And now you say, why are zero-knowledge proofs important today? So for example, let's say I want to convince you that I'm who I am. So, when we enter web pages and so on, you need some authenticity. You need to know some people you allow to enter, some people you don't. So I want to convince you. Usually the way it works is I convince you I have some secret key, and this secret key is authorized. So let's say one way this is done is, there's a bunch of kind of public keys that are authorized to enter the web page, and now I want to prove to you that I hold one of the secret keys. One of the secret keys of these public keys is mine, and therefore you should let me in. I can give you my secret key. Now you say, see, this is my secret key. It's very easy to see that a secret key corresponds to a public key. It's kind of paired. So I give you the secret key. You see, it corresponds to, and you're happy. But I don't want to give you my secret key is my identity. With my secret key, you can go to my bank account. You can go, so what do? I give you zero-knowledge proof. So a lot of the way cryptography is used today is via these identification protocols or kind of signature protocols that use these zero-knowledge proofs.
If you can really do that, then it implies some universal theorem for cryptography. There are many different cryptographic tasks. You want to sign documents, you want to exchange secrets, you want to play poker on the telephone. I mean, there are very fascinating examples. You want to do voting. How do you do everything digitally without any physical means? And for different such tasks, different protocols were designed. And in these protocols, you have to protect against people who don't play fairly, about people who want to destroy, people who want to vote twice, people who want to have an ace in their sleeve, and so on. And zero-knowledge proofs allow to get rid of this problem in general, in the very simple way. You just demand every player in its turn to prove that they are acting according to the protocol. And of course, this behavior depends also on their secret. But if they prove it in zero knowledge, they don't divulge their secret. So there's a way, an automatic way to enforce the correct behavior to any participants of any cryptographic protocol. So that was one major implication. People use it in, one thing that was worrying at the time is the practicality of this, because it was quite complex and heavy computationally, but also to my amazement, there are applications that are run every day, including in blockchain technology and digital cash, which have zero knowledge embedded in them, so people made it efficient. But people find even more ingenious applications where they took this idea to completely other settings, not digital but physical. There are zero knowledge protocols for nuclear disarmaments, for example, developed by Boaz Barak and some physicists that where how do you prove to for Russia and the United States that you really dismantle this nuclear missile. Applications to DNA testing. I mean, you want to make sure that if you sample DNA from many people suspected of a crime, you want to make sure that, if the guilty party is there, is fine, you catch them. But if all the other people, then knowledge of their DNA should disappear from the system because you don't. So you want zero knowledge proofs of whether the DNA matches the synopsis.
So this is really kind of became a little bit, I would say, the bread and butter of cryptography. But moreover, a very interesting consequence of this line of work, which I think was unexpected, is that once they considered this model of interactive proof, so now we have a new proof model. What can I do with it? And it turns out that proofs can be made much, much more succinct in this kind of interactive proof model. So think about some theorems or proofs. If you give a classical proof, they're going to be very, very long, so long that it's kind of infeasible to verify. Using an interactive proof, you can make it very efficient to verify. So these proofs became much more efficient. And today what we know how to do is actually, it's kind of an interesting story, but today what we know is how to take these interactive proofs and then eliminate the interaction using cryptography. So that's kind of, we start with an interactive proof. Nothing about it is hiding or crypto or anything. So the idea is, I'll create an interactive proof, and then there's kind of a generic way known as the Fiat-Shamir paradigm. It's a paradigm in cryptography to eliminate interaction. So kind of this zero-knowledge proof, it kind of defined a new interactive proof model. A lot of theory and beautiful mathematics were developed to kind of show that this model is very powerful. Namely, you can prove very kind of theorems that usually require, that classically require very, very long proof. You can prove them very succinctly. And then we kind of show, actually, don't worry about the interactive setting, that it's not really, that it's problematic. We'll eliminate the interaction at the end using what we call hash functions, some paradigm. So at the end, kind of this journey brought us to just very succinct kind of cryptographic proofs. And these succinct proofs are actually very useful, in particular in today's world where a lot of there's tons of data and tons of large-scale computation that, for example, they're used a lot in various blockchain and cryptocurrencies because I need to verify that the transaction is good. How can I verify it? To verify a transaction is good is a huge computational burden. So kind of attaching these succinct cryptographic proofs is a way to kind of attest to the correctness of a transaction. So these kind of schemes are becoming more and more popular these days, and my research is actually more on these kind of succinct proofs. Yeah.